Good day everyone. Welcome to this presentation on methods of chemical analysis in metallurgy. In this lesson, we will look at two major categories of analysis methods. The classical methods, which are the traditional chemical techniques developed many years ago, and the instrumental methods, which use modern machines and technology. Both approaches play an important role in determining the quality and composition of metals and ores. Classical methods of analysis. Copper assay. Copper is one of the oldest metals known to humans, and determining its amount in ores or alloys is very important in mining and metallurgy. The traditional copper assay can be done in two common ways: electrolytic deposition and iodometric titration. In electrolytic deposition, the copper from the solution is deposited onto a cathode using electricity. The mass of copper that collects on the electrode can then be weighed to know exactly how much copper was in the sample. On the other hand, in iodometric titration, iodine is used to react with the copper in the solution. The reaction is measured by titration, which allows chemists to calculate the copper content. These classical methods may take time, but they remain reliable and are still used in many laboratories for accuracy. Lead assay. Lead assay is usually performed on lead ores such as galena. One of the common ways to test lead is through the gravimetric method. In this process, the lead in the sample is converted into lead sulfate by adding sulfuric acid. The lead sulfate, which is a white solid, is then filtered, dried, and carefully weighed. Because the mass of the lead sulfate is directly related to the amount of lead in the sample, this method gives a good estimate of lead content. Even though this procedure looks simple, it requires patience and careful weighing to avoid errors. Zinc assay. Zinc is another important metal, often used in alloys and galvanizing. The classical method for zinc assay is usually done using complexometric titration with EDTA. Here's how it works. The zinc ions in the solution react with EDTA, a special chemical that forms stable complexes with metals. The amount of EDTA used to complete the reaction tells us the amount of zinc in the sample. This method is quite popular because it is accurate and easy to perform once the sample is prepared properly. Iron assay. Iron is one of the most important industrial metals. In classical analysis, iron assay is usually performed using a redox titration with potassium permanganate or CuMnO. First, the iron in the sample is dissolved in acid. If the iron is in the ferric form, or Fe, it is reduced to the ferrous form, Fe. Then, a purple solution of potassium permanganate is slowly added. As long as there is iron present, the purple color disappears because the permanganate is reacting with the iron. Once all the iron has reacted, any extra drop of permanganate will keep the solution slightly pink. That point marks the end of the titration, and from the amount used, the iron content can be calculated. This method is widely used because it is simple, visual, and dependable. These classical methods have been the foundation of chemical analysis for centuries. They rely on careful weighing, titration, and precipitation reactions. However, with the development of science and technology, more advanced and faster methods have become available. Let us now move on to the instrumental methods of analysis, which use modern equipment to achieve higher accuracy and efficiency. Spectrophotometry. Spectrophotometry is a modern method of analysis that is based on the interaction between light and matter. The principle is simple. Different substances absorb light at different wavelengths. In practice, a sample solution is placed in a small container called a cuvette, and light is passed through it. The machine measures how much light is absorbed. From this, the concentration of the substance in the solution can be calculated. For example, in iron analysis, a chemical called thiocyanate is added to the solution. It reacts with iron to produce a bright red complex. The spectrophotometer then measures how intense the color is, which directly corresponds to the amount of iron present. This method is very useful for detecting even small amounts of metals with high accuracy. X-ray diffraction XD and X-ray fluorescence XR. Another important group of instrumental methods involves the use of X-rays. These include X-ray diffraction, or XD, and X-ray fluorescence, or XR. XD is mainly used to study the structure of minerals. When X-rays hit a crystal, they are diffracted in specific patterns that act like a fingerprint for that mineral. This helps scientists identify what minerals are present in an ore. On the other hand, X-surf is used to determine the elements present in a sample. When X-rays strike the sample, they cause the atoms inside to emit secondary X-rays. The energy of these emissions tells us which elements are present, and their intensity shows how much of each element is there. Together, XD and X-surf provide very powerful tools for both identifying minerals and analyzing their composition, and they are widely used in mining industries for fast and non-destructive testing. Microanalysis. Microanalysis refers to techniques that allow scientists to study materials on a very small scale, sometimes even at the level of individual grains or crystals. A common instrument used is the scanning electron microscope with energy dispersive X-ray spectroscopy, or SEM-EDS. In this method, a focused electron beam scans the sample surface. This produces high-resolution images that reveal the texture and structure of the material. At the same time, the interaction of the electron beam with the atoms in the sample generates X-rays, which can be analyzed to identify the elements present. Microanalysis is especially valuable for understanding the distribution of trace elements in ores, studying inclusions in minerals, or checking the quality of alloys. It combines visual imaging with chemical analysis at the microscopic level. In summary, we have seen how both classical and instrumental methods of analysis contribute to metallurgy and mining. Classical methods, such as copper electrolysis, lead gravimetry, zinc titration, and iron permanganate titration, are traditional techniques that provide accurate results through careful laboratory work. Meanwhile, instrumental methods such as spectrophotometry, X-ray diffraction and fluorescence, and microanalysis make use of advanced technology to deliver faster, more precise, and detailed information. Both approaches complement each other. Classical methods teach us the fundamentals, while modern instruments provide efficiency and higher sensitivity. Together, they help scientists, engineers, and industries ensure that metals are properly analyzed, making mining and metallurgy more effective and reliable. Thank you for listening.